I'm Mark Callahan, and here to share updated results from the performance work that I do on MyRocks. For many years, there was only InnoDB, and I did a lot of performance evaluations and debugging with InnoDB. I didn't work for the InnoDB team, so I was free to speak my mind about the good and the bad part of InnoDB. I wasn't on the product team, so I wasn't necessarily marketing from the product perspective. Now I'm on the RocksDB MyRocks team. I work directly with people working on the engine, so I'm learning that it's not as easy to speak frankly about database engine performance when it's your own product. I am proud of it. Sometimes I share information to show other people that it's actually a good engine. Other times I do publish results to motivate the team to fix some problems that I hope we fix. But it has been a learning experience for me as I've moved to the product side. There have been a lot of improvements to RocksDB. Improvements to RocksDB make MyRocks and MongoRocks better. And we've also been improving MyRocks quickly, so fast that it's hard for me to do a lot of performance evaluation of everything listed here. And in some cases, I have results showing the direct impact of these features, but I'm falling behind. Recent really has been, I think, since I last spoke, we have bulk load optimizations, a fast path to insert data. The motivation for this is to make InnoDB to RocksDB or to MyRocks migrations happen faster. These are directly building the LSM, the max level of the LSM tree, without going through the standard compaction pipeline and without going through the mem table. Direct I/O for a long time, like LevelDB, RocksDB is based on buffered I/O. We have customers who want to use direct I/O, people who do database performance monitoring like direct I/O. I like to know what operation really did a disk read, which I can't determine when it's when I'm doing buffered I/O page reads. Smarter compaction. We have some documentation debt, so I don't think this has been fully described in public, but the net result is we are seeing a 2x reduction in write amplification for real workloads and for some of the synthetic benchmarks that I run. Support for database much larger than RAM. We have fast storage devices, so we like to run I/O-bound workloads because we want to minimize the amount of memory required for the database tier. For a long time, I think database larger than memory meant about a 10 or 20 to 1 ratio. We are moving towards, we want to be effective at 100 to 1 and 200 to 1 ratios between database size and memory. The challenge now is where we used to be able to assume that everything in the LSM tree was in memory except for the bottom level of the LSM tree at a 10 to 1 ratio. We no longer can assume that. So multiple levels of the LSM tree might not be in memory. Additionally, we used to be able to assume that all of the indexing blocks and the Bloom filter blocks, we used to assume that they were in memory. At 100 or 200 to 1 ratio, that's no longer true. So we have some algorithmic work that's in progress to be effective in this case. Response time variance. I've been failing to publish enough data on this. I have a couple of blog posts, and Procona eventually might be showing it. InnoDB used to have a lot of jitter. And Procona, one of their great contributions to the MySQL community was documenting and helping to fix the jitter that InnoDB had. And by jitter, I mean occasional response time stalls. For InnoDB, the problem was page write back wasn't fast enough. And some of that was a CPU bottleneck. It wasn't just an I/O issue. We have some jitter in MyRocks that we need to fix. It took a long time to fix this for InnoDB. My claim is we're going to do it much faster, like within the next year. Already today, the worst case response time outliers for MyRocks are much better than they are for InnoDB, and I can show that with some benchmarking. Blind deletes, for some workloads that want to delete quickly, if the delete command doesn't need to know the number of rows that were deleted, then we can perform the end. If there's only a primary key, we can perform the delete without a read. So it's much faster. Time to live, it's an even faster way to delete data. If the end user can specify the time to live for the data that they insert to the database, then we can figure out when to remove it during compaction. So it's just removed for free. And there's just a lot more done and a lot in progress. One of the problems is we have some documentation debt in MyRocks. We really need to catch up to the engineering effort that's taking place. So compaction, I said we had some work that cut write amplification in half. We like options in MyRocks. We have lots of options. Sometimes that's good. Here, the option name compaction pri for priority equals k-min overlapping ratio. Long name. Don't worry about the name. Look at the impact. So 3 workloads: insert benchmark in memory, insert benchmark IO bound, and link bench, which is social graph transaction processing, IO bound. Reducing writes to storage by 35 to 54%. Essentially, we're compacting less data. We've figured out how to reduce the amount of data we need to compact. Now, if we're compacting less data, we're not just saving on writes, we're saving on reads from storage because compaction has to read data from storage. We're also saving on CPU because compaction uses a lot of CPU. And in this case, we're saving between 4 and 25% of the CPU overall load on the server from this change. Another one, bulk load. This is in-memory insert benchmark, so write heavy. From a storage perspective, nothing is getting read from storage. I have results at 1, 4, and 16 clients, comparing MyRocks from MySQL 5.6.35, MyRocks with bulk load from 5.6.35, InnoDB from MySQL 5.7.17. So this is the much better version of InnoDB. At 1 client, with and without bulk load, MyRocks has similar performance. It's ahead of InnoDB. At 4 clients, bulk load begins to show benefit. MyRocks is still ahead of InnoDB. At 16 clients, InnoDB 5.7 begins to shine. A lot of work has been done to improve InnoDB. So MyRocks without the bulk load optimization saturates the rate at which we can move data through the mem table. However, with the bulk load optimization, you can see that, and it's slightly over 500,000 inserts per second in this case. The green line, this is what's allowing us to migrate faster, and the person clapping is one of the people who, in operations, the PE team, who is happy that we can quickly move, change from InnoDB to MyRocks because we have a lot of data. So why MyRocks? MyRocks was started, the reason we staffed the team was for not link bench, for the user database tier. Social graph transaction processing. The vague number we share in public is one of the numbers was many tens of petabytes. So it was a large enough workload that we were willing to staff a team to build a new MySQL storage engine. But it's not just for that workload. We have other internal workloads that are moving to it. And we hope and expect external workloads to move to it once it becomes available in AliSQL, MariaDB Server, and Percona Server. The real reason for us is best space efficiency. So we want to use less space. The leveled compaction, the leveled LSM algorithm is, I don't want to use the word optimal because I can't prove it, but it's significantly better than a B tree. Better write efficiency. So we write less per transaction back to storage. Writing less means you can use lower endurance SSD or the SSD lasts longer. Best space efficiency means we use less SSD. Good read efficiency. Good is a vague term. And does it mean good enough? In some cases, with the LSM algorithm that we use, we sacrifice CPU efficiency and potentially I/O efficiency to achieve these other goals. But it's not always the case. For the production workload, we are matching InnoDB for throughput and response time. And for the production workload, we are using half the space versus compressed InnoDB. We are using 1/4 the space versus uncompressed InnoDB. So this is our motivation. Initially, the write rate to storage was about 1/10 versus InnoDB. With the new compaction algorithm change, that comes down to about 5% the rate of InnoDB. So InnoDB is writing potentially 20 times as much back to storage per transaction. And we're doing this with similar performance. There's a lot of reasons for why we get better efficiency for space and write, and occasionally for read, versus a B tree. The big reason for space efficiency is leaf nodes on a B tree fragment, subject to random operations. With InnoDB, they frequently become half full. Half full pages on storage means you're using twice the storage as optimal. Half full pages in memory means you're wasting half of your memory in the buffer pool. Compressed InnoDB still suffers. It uses a fixed page size on disk. If you take a 16K page in memory, compress it to 5K, if you're using 2x compression for InnoDB, you still round up and write out 8K. So you're losing some of your compression. Per row metadata, InnoDB has more, and it's not compressed if you're using InnoDB compression. With RocksDB, the per row metadata we have is less, and most of it's compressed to 0 bytes. Key prefix encoding, which is applied for both compressed and uncompressed pages, means we use less space for indexes, for the keys, both in memory and on storage. For write efficiency, the really key thing here is that we run I/O-bound workloads. We don't keep the working set in memory. That would be too much memory. So we do a lot of reads and writes. The worst case for a B tree is when you're evicting a dirty page that only has one row that's been modified. The write amplification is the ratio of the page size to the row size. This happens to us in production. Let's say we have a 256-byte row and a 16 kilobyte page. That's the write amplification from that is a factor of 64. Then add in the double write buffer for InnoDB, and now we're up to write amplification of 128. So the LSM wins across the board for write efficiency. For read efficiency, if you look at the algorithm, what it's doing, you have the potential to do more CPU work. And for range queries, you have the potential to do more I/O with an LSM. But in practice, it gets more complex. The first is we put more data in cache, in memory. The B tree, you're caching fragmented pages. You're caching half-full pages. You're wasting memory. If you had to use the notion of fragmentation with MyRocks, it's about 10%. It's not half. There's also less data to cache. We just are more effective in how we encode data. Bloom filter means you're not doing disk reads for keys that don't exist. In some cases, we've had workloads that were wasting a lot of I/O trying to search for keys that did not exist in the tree. Another important thing is that when you spend less on writes, you have more I/O capacity to serve reads. So if you're approaching the saturation point, a more write-efficient database makes reads faster. And the last point, if you're update heavy, if you're doing a lot of index maintenance, non-unique secondary index maintenance is read-free. With a B tree, secondary index maintenance, read the page, modify it, make it dirty, eventually write it back. With MyRocks, if it's not a unique secondary index, we don't have to read anything. It's just a blind write into the mem table. And it makes it MyRocks significantly faster for many update-heavy workloads. So I use the term benchmarking to describe the action of saying X is faster than Y implies X is better than Y. And it's also the practice of using unexplained benchmark results to motivate your customer demand or interest. I don't have time to explain all of the results I have, so I'm definitely doing some benchmarking here. But I do have the data, and it's in my slides. I'm just not going to explain all of it. But really, for me, when I talk about performance, I want to talk about throughput, efficiency, and quality of service. I don't just want to show one bar that says, this did X requests per second, this did Y. I want to be able to explain what happens. Here is the result with MyRocks that it has, in this case, the average throughput is about 150,000 per second. It's a pretty good result. So if I just showed one bar with 150,000 and compared it to another engine, you might be impressed. The problem here is there's some variance. This is from a few months back. We've done some work to make it significantly better, but we still have some variance to fix. And so when I say performance is complicated, that's what I mean. You want to see the full picture. But now I'll jump into benchmarking. Just one bar per engine. It's kind of hard to see the full picture. Link bench is the social graph workload that is it's a benchmark based on what we do in production. It's open source. Here I tested MyRocks with and without compression, InnoDB with and without compression, TokuDB with and without compression. MyRocks is the fastest, so it's clearly the best. InnoDB with compression on link bench actually does pretty good. I was surprised. I've been surprised by this. TokuDB, not as good on this workload. Now, Percona might not be motivated to fix Toku for link bench because no customer is running it, but just I've been hesitant to speak about Toku in the past because people I respect worked on it back then and still work on it. So I'm hesitant. But I do want to share, because people do ask me, why didn't you just use TokuDB? Here's one reason. So benchmarking, here's all the data I collect. And for me, this is a typical performance report. First column is transactions per second, the average rate, which can be very misleading because it can hide the variance. Second column, how many disk reads per transaction do I do? It's a measurement of read efficiency. Third column, how many kilobytes from I/O am I reading per transaction? Next column, how many kilobytes of I/O am I writing per transaction? And then just it's a bogus metric in terms of the units, but how much CPU do I use per transaction? Ignore what the units are, it's just for relative comparison. Next column is the database size in gigabytes. Next column is MySQL process size, RSS. So how much memory is it really using at the end of the test? And the last column, in this case, is the 99 percentile response time for the most frequent operation in link bench, which is a range query. And before I mention range queries can be a problem for an LSM, but here we have by far the best response time for range queries in link bench. MySQL InnoDB is using more RAM because I give it more RAM. MyRocks and Toku use buffered I/O, so I set the buffer pool to be smaller to let them benefit from the buffer pool. Database size in gigabytes. If you look at MyRocks with zlib, it's about 1/2 the size of InnoDB with compression and about 1/4 the size of InnoDB without compression, which actually matches what we see in production. The really big deal, I/O kilobyte written per transaction. This is with the latest change that cuts write amplification in half. MyRocks is close to 1. InnoDB without compression is 18 to 19 or 20. InnoDB with compression is 14 to 15. This is measured from I/O stat. If I also accounted for the I/O done from flash firmware garbage collection, that ratio would increase. I've measured it in the past. It might go up to 30 to 1. So if you have a write-heavy application, MyRocks is a nice fit. Insert benchmark. I've been using this for a decade to make database engines fall over. InnoDB fell over, MyRocks fell over, TokuDB fell over, WireTiger fell over. I got a community member, contributor of the year from MongoDB, I think twice, for filing performance bugs for WireTiger, mostly from this workload. I run it in a special way, but I load some data, and then I run inserts concurrent with queries. And the fallover usually happens when you watch the database engine try to do inserts and queries at the same time. So here, database is definitely I/O bound in this case. MyRocks and Toku, not surprising, do great on this. InnoDB 5.7 is not that much better than 5.6. Without compression, there is some difference, but in the past I've had people say, you're not sharing results for InnoDB 5.7. Well, I've begun doing that, and I'll do it more. And in many workloads, I/O-heavy workloads, there's not enough of a difference compared to a write-optimized engine. The other thing is when we go over to inserts concurrent with queries, the blue bar is inserts per second. I've rate limited it. So the goal is to sustain 16,000 inserts per second, queries as fast as possible. You can't really see it here. I'll show it on the next slide. Toku can't do 16,000 per second. That's a problem. Toku, when you do read heavy with write heavy mixed together, some problems show up. Here's one example. The green bar, queries per second. Major difference between MyRocks and everything else. Major difference. And so just something I'm happy about. If I look at some of the performance data, I said TokuDB was unable to sustain the insert rate. If you look at the average insert rate, the first column for Toku, it's 15,000. Oh, those are actually wrong slide. Next one. 14,818 and 15,152. 15,845 is about the max you can get from the way I try to sustain the rate. So Toku was unable to keep up. One other interesting thing is if you compare MyRocks with zstandard, TokuDB with zlib, TokuDB is using about 1.2x more space. I don't fully understand the Toku algorithm, but my perception is they're favoring writes, and so they're accumulating more old versions of data, where MyRocks is very strict about how much old data it would have to minimize space amplification. Some artifacts that I saw when I compared the same benchmark, same hardware, except for the storage, moving from fast to slow SSD. Blue line is fast SSD, green line is slow SSD. MyRocks, blue to green, is not losing that much. InnoDB 5.6, and it losing a lot. When you go from fast to slow SSD, InnoDB is very dependent on random I/O throughput. The slow SSD has about 1/10 the IOPS of the fast SSD in this case. InnoDB 5.7 sustained a little bit better, but MyRocks is for this workload is immune to the random I/O demand or capacity. Another interesting artifact, I repeat the test with one table rather than 16 tables to see if things change. For the load, MyRocks performance it decreases a little bit. InnoDB performance improves, moving from 16 to one table. Toku suffers, blue to green, moving from 16 to one table. I didn't try to debug this, other than, it's contention. I'm not sure if it's the way they're doing I/O. I don't think it's CPU or mutex contention. Same benchmark, but in-memory workload. So there's no storage reads, only storage writes. TokuDB, again, shows the same problem. Blue to green, performance drops. MyRocks and InnoDB, mostly okay, although InnoDB in 5.7 is having a fall off there. I do a lot of cross-product testing, so change one option at a time, go from 16 tables to one table, go from fast storage to slow storage. Takes a lot of time to run the tests, but I notice some interesting things. Last set of benchmark results, Sysbench, everyone's favorite workload. Very synthetic. You need to be careful with what you do. Very configurable. So I run about 10 different workloads via it. Most people only run the OLTP read-write. So first workload, I'm running at 1, 16, and 48 clients. My hardware has 48 threads. So I have enough CPU for this. Update only with secondary index maintenance. Great workload for MyRocks. top 2 lines are pretty good. InnoDB shines with concurrency. Very happy. The InnoDB performance guru is in the back row. So thank you. Or Toku doesn't do as well with that workload. InnoDB with compression suffers horribly, horribly. And I think it's the per index lock. OLTP read-write, traditional workload everyone runs. The key here is the range query length. Shorter range queries are better for MyRocks in this workload. Longer range queries, MyRocks can begin to fall off. We have some work to do. We need to catch up with InnoDB 5.7 here. We're ahead of Toku. InnoDB compressed, not on the map. OLTP read-only. This, not my favorite workload. There's some things I could do to make MyRocks look great here that I might not admit to. If you're running a read-only workload, the problem is this read-only workload shows up after a read-write workload, and so MyRocks doesn't yet dynamically adapt to the changing workload to optimize its file structures to account for that. So MyRocks is not leading the way here. When we go to larger range queries, you see InnoDB gets a larger advantage because of the CPU cost of evaluating the range query. Sysbench point query, not as hard for MyRocks to do. InnoDB 5.7 is still leading the way. MyRocks is competitive. And then finally, insert only. Again, great improvements for InnoDB in 5.7. So we have work in progress. We're going to catch them on this. Thank you. That is all of the data I have. And I'm happy to talk afterwards.